So, welcome back. This video is the first of a long series of videos we'll have about compact topological spaces, compact metric spaces, and consequences of space being compact. So, compactness, the way we'll think of it anyway, right? So, our main use for compactness would be to consider minimization problems like, oftentimes in mathematics we have problems which are like given a certain function f from some space to R, or maybe, this function could take other infinite values or something like that. You want to find an S star in S such that the value of f at the point S star is as small as possible. Right, what are examples of this problem? You want to minimize a function over a subset of Rd, that's the problem. You want to find the curve of smallest possible length connecting some points of the sphere, that's another problem like this. Well, anyway, there are many problems that can be cast in this form. And the constant of compactness for us will be something that guarantees that if f satisfies some minimal condition, like it's continuous, or if it's lower semi-continuous, which is something we're going to mention today, then at the very least, you know that such a point S star exists, that the infimum of f is achieved, right? So compactness guarantees that if f is continuous or satisfies some related property. But what is compactness? Well, the definition in the setting of topological spaces is kind of clumsy and abstract, and that's the main subject of the present video. So here's the definition. I have a topological space, so X and its open sets. X is said to be compact if for any collection of open sets that covers X, there exists a finite subcollection that also covers X. I mean, by covering, I think it's clear what I mean. The union of these open sets is equal to X. So if you have any collection of open sets whose union is equal to X, there is a finite subcollection that also covers X. So this is a definition that asks what it means for a whole space, for a whole set X to be compact. It could ask, if I want to talk about subsets of X, what definition do I have? Well, I mean, if you have a subset K of X, then you just use the relative topology. And then it turns out that in this case, you want to say that if K is contained the union and is covered by collection A, so here I don't have equal, I have contained, then K is contained in B, A and B, A, B finite. This is a bit hard to read, but hopefully you can understand what I said. So anyway, let me erase this and say it again. So when you replace X by a subset of X, then you can write everything in terms of the related topology. But maybe I should just mention A opening K means that, just to remind you, that A equals K intersection A tilde, with A tilde being an open set of X. So if you recast this definition here, I'd say something like, if K is contained in the union of open sets of X, then there's a finite collection of these sets that still contains K. Okay, but right now we're going to be dealing with this abstract definition, and our main result will be that if a topological space satisfies this abstract definition, then any continuous function defined over the space achieves its infimum and its supremum. Okay, but before we get to that, we need to prove a few preliminary results about this definition. And so let me start with one of them, which is just a restatement of this. So usually when we talk about definitions involving topology or general topology, we have one version of the definition about open sets and another one about closed sets, right? So remember that we proved that the union of any collection of open sets is still open, and therefore the intersection of any collection of closed sets is still closed. So now that we have this, we want to find a version of this definition that involves closed sets. And okay, that's our proposition here. So and if a space is compact, if and only if it has the finite intersection property. So what is this? If I have a collection of closed sets, then the intersection of these closed sets is non-empty if and only if for any finite subcollection, and non-empty, right? So otherwise it's not much fun. I have that the intersection of this finite collection is also non-empty. So in some sense, this maybe looks even weirder than the original definition, but this is going to be very useful for us. So bear with me, and we'll get through this together. Right, so what is it saying? I mean, okay, I'm going to explain in different forms, right? So take a collection of closed sets. Suppose you want to know if this intersection is non-empty, if there is a point that belongs to all these closed sets. What the finite intersection property says is that if you can check that intersections of any finite subcollection of these closed sets are non-empty, then the whole thing has non-empty intersection. So it's a very strong fact, and for instance, this criterion implies that the real line is not compact. And I'm going to mention this because we're going to use this later. Right, so assuming the proposition, let's prove that R is not compact with usual topology. And what we're going to show is that it doesn't satisfy this finite intersection property, right? How do we prove that the real line is not compact? Well, I'm going to take my collection of closed sets to be all half-infinite intervals that half infinite to the left and closed to the right. So these subsets are closed, right? If I take the intersection of everybody in this family, that's empty. Why? Right? Because take a point in the real line. Clearly, there's some interval of this form that lies entirely to the left of this point. Therefore, for any value t in the real line, there is an interval of this form that does not contain t. For instance, the interval from minus infinity to t minus 1, say. Right? So when I take the intersection of all intervals, it's clear that all points are going to be outside it. Right? So the intersection is empty. But if I take any finite collection of these intervals, right? So if I take anything like this, what is this? So it's, okay, each interval I'm saying, well, these are all points of the real line. They're either equal to xi, x sub I, or to the left of x sub I. So when I take these intersections, just think a little bit about it, and I have another interval of the same form where now the right extreme, well, the left extreme is still minus infinity. The right extreme is just the minimum value amongst these guys. So any finite intersection of these intervals is going to be non-empty for this reason, right? This is going to be useful later. Here's an exercise I want you to do. It's in the lecture notes, and unfortunately in Portuguese. It has a very similar proof. That intervals of the form, say, I don't know, A, B, are not compact. And you can use the finite intersection property more or less the same way, except that maybe you have to deal with the induced topology of these intervals, but that's not really a major problem. So, okay, at the very least, we understand that if the proposition is true, then we have a good criterion for being able to tell when a topological space is non-compact. In some cases, it's going to easily give us that. To prove that something is compact is something that we're not going to emphasize in the setting of general topology. We're going to quickly move to the metric realm, and there we're going to have criteria that we can use. But let's leave it like that right now. So I'm just interested in these abstract results that I can prove easily via general topology. So let's prove that that compactness is equivalent to this finite intersection property. And really, this is yet another example, right? As I said before, when we do things in point set topology or general topology, we are always doing things in two versions, one with open sets and the other one with closed sets. And the way we go from one to the other is by taking complements, right? The complements of closed sets are open, complements of open sets are closed. Complement of an intersection is a union. Therefore, we can see that there's some sort of relationship between these two things. And basically what I'm going to do in the proof is just write down this relationship, and then everything should be clear. Okay, how do I make a correspondence between collections of open sets and right? So this is a collection of open sets, a collection of closed sets. Well, all I have to do is I say if I have an open set here, I take a closed set that's a complement, right? So this is the correspondence. A collection of open sets naturally corresponds to a collection of closed sets. Okay, now watch. If I want the union to cover X, meaning, right, that's a property that defines compactness. If I want the union to cover X, then this is equivalent. Okay, take the complement here, right? So the complement of a union is an intersection, and then you get a complement, which is like F. And what's the complement of X? Well, the complement of X is the empty set, right? X is everything, so the complement of everything is nothing. So this property here is equivalent to saying zero. To say, sorry, that the intersection is empty, right? So just, again, I'm just saying I take the intersection of a complement for all A in my collection. That's the same thing as taking the intersection of F for all F in my collection of closed sets. And so the saying that there exists a collection, a subcollection, right, of the open cover that is finite and still covers everything is the same thing as saying that there exists a subcollection of the closed sets such that intersection of F belonging to G, F is empty set, right? Again, I'm just taking complement. Suppose there's this subcollection that's finite whose union covers X. Now I take complements, right? So X complement we know is the empty set. And here I get an intersection of a complement for all A in this collection. And that's like saying I take a finite collection of the closed sets and take this intersection. And that goes both ways, right? So there shouldn't be any problem with this. Okay, I claim that basically our proof is here in all these diagrams, right? So suppose that I have a compact space, and now I have a collection of closed sets. Now I claim that these closed sets have non-empty intersection if and only if any finite subcollection has an empty intersection. How is that? So let's prove the other way around, right? So if the intersection is empty, right, I'm just negating everything, there exists a finite subcollection whose intersection is empty. And how can that be? Well, it's clearly over here, right? So the intersection of the closed sets is empty if and only if the corresponding collection of open sets covers X. And because the space is compact, if this happens, then there's a finite collection that covers X, and therefore there's a finite collection of closed sets, that has empty intersection, just like the full collection. And it's clear to how we go the other way around, right? So if you have this property, then that means that all open covers have finite subcovers. So and that's it. Again, that's as many things involving switching between open and closed sets. All we need are these laws relating complements of unions to intersections and complements of intersections to unions, and the very basic fact that complements of open sets are closed and complements of closed sets are open. Okay, so far so good, right? So this is a finite intersection property, which, as we saw, gives us an equivalent definition of what a compact set is. Compact topological space. Okay, so now I'm going to do something different, which is in some sense, it's not something we need to prove this theorem about continuous functions, which I mentioned, but it's something good to know. Well, it's actually two easy properties, right? So, but this one is good because it's going to allow us to, to get more compact sets out of some specific compact set. So what do we mean? Prop 2, if X tau compact, and you have a closed subset of X, then K is also compact where this is the induced topology. Okay, how do we prove this? It's really kind of simple, okay? So I'm just going to draw a picture of the proof, and hopefully you buy it. So here's my space X, and there's a part of it that I'm considering, which is K. And we're assuming K is closed, therefore A, which is K complement, is open. What do we have to show? As I argued before, we have to show that if we have a collection of open sets of X, right? So, and K is contained in the union of these guys. So remember, there's a little exercise to argue that saying that K is compact in the induced topology means that this should be true, right? That for any collection of open sets of X, if K is contained in the union, so K is covered by this collection, there exists a B contained in a finite K contained a B. Okay. And yeah, so let me actually call this complement here A hat, just to make it clear that that's not one of these sets. Or even better, let me call this O, right? So O is K complement and O is for open. Okay? Okay, we have this. Now my point is that if this collection A covers K, right? So we have these open sets, which are maybe like this and this and this and this. Okay, everything should be in sets, right? So forgive me for my bad drawings, but hopefully you're used to them by now. Here I have A. If A covers X, right, all I know is that X is compact, so that has to come into play somehow. My claim is that if A covers X, then A tilde, which is simply equal to A union K complement, which is O, covers the whole space. What do I mean by that? So remember, my assumption is that I have this collection of open sets that covers K. So K is contained in the union. What about X? Well, all points of X are either in K, and therefore they belong to this union, or they're in K complement, and therefore they belong to O, right? So all points of X are contained in this collection of open sets consisting of this original collection covering K, and this extra open set, which is K complement. Okay, why is this good? Because now we have an open cover of X, and therefore it has a, okay, so I'm going finite covering X. So now I can say, okay, we can replace this A tilde by a finite subcover. And the little exercise which I'm going to leave you is to prove that if I take B tilde, right? So remember, I added an open set to cover the whole of X. Now, if I remove this open set, my claim is that I get a cover of K. And is this finite? Of course it is, right? So because if B tilde is finite, I'm removing an element that's still finite. So the main point being is that since K is closed, that was fundamental. If I have an open cover for K, I have an open cover for X, which I obtain by just adding this open set, which is K complement, to the open cover of K. And therefore, I can relate open covers of K to open covers of the whole space. Notice that I strongly use the fact that K is closed, but that's one of our assumptions. So, okay, in a nutshell, we've just proven that closed subsets of compact spaces are also compact in the induced topology. Okay, so that's one result. Let's prove another result now. Another simple result like this, which is that, oh, by the way, there's also proof of this using the finite intersection property, but I'll spare you on the details. So our next result is going to be about images of compact spaces by continuous functions. So remember that we showed, okay, here's one thing that we know from early on. We proved that we have a continuous function, then pre-images of open sets are continuous. Actually, that's a definition of what a continuous function is in the realm of topological spaces, right? Pre-images of open sets are open. Now, for connectedness, we proved something that was in the other direction. We proved that if we have a continuous function defined over a connected topological space, then the image of the set, right, of this connected space is also a connected topological space. And now we're going to prove something different here. We're going to prove something similar, for compact metric spaces, which is that if I have a topological space, this should be Z here. So let me actually call this tau Z like we do with the metrics, right? We just have a subscript and that distinguishes, okay, that means this is a topology of Z, this is a topology of Z. So here I have a topological space, and I have f from X to Z continuous. Then I claim that f of X is compact. And this I'm really going to sketch. The other one I said I was going to sketch, but I basically proved it in full. How do we prove this, right? So we have our compact X here. We have Z, which is something else, could be non-compact. But here we have f of X. And I have f, which connects the two. Now assume that I have an open cover of this guy. So bunch of open sets covering the space, covering f of x. Now I claim that when you look at the pre-images of these guys, so let me call this A tilde, f minus 1 of A in calligraphic A. This is an open cover of X. And why is that? Well, okay, if I take any set here, A, I know that f minus 1 of A is an open set, right? That's just using continuity of f. So for a single set, I have f minus 1 of A. Now, so this means this is a collection of open sets in X. How do I know that they cover everything? Well, I just take a point here, X, and it should be in some preimage. So I just do, okay, F goes to f of X. F of X is covered by this collection, right? This collection covers the whole image. Therefore, there exists this A X containing X. And that means that X is contained in f minus 1 of A sub X. Okay, so I'm done, right? So I know that all elements of the space X are contained in some preimage. So this is an open cover. And how do you finish the proof? Oh, our assumption is that X is compact. So this open cover has a finite subcover. And what we have to do is to show that the corresponding guy over here is a finite subcover of f of X. Right, so this means that right, because X is compact, there's a finite subcover. And now what you have to do is to find a B contained in A, and that's easy. Okay, this collection corresponds to choosing some open sets in A, calligraphic A. So yeah, it's a finite number of open sets here. Take these sets here, they cover the image. And then you're done. Then you can show that the image of any compact topological space by a continuous function is also compact. Okay. Right, so now we move on to the more important theorem. I mean, this is important too, very important actually. But the main thing is that I wanted to get to is this proof that continuous functions always achieve their infima and their suprema over topological spaces. A continuous function, so the space to R, right? So there's some restriction there. I'm actually going to prove something slightly more general. So I have, okay, X is my compact topological space, right? And I'm going to assume that this function is lower semi-continuous, meaning that for any t in the real line, f minus 1 minus infinity t, the subset of X is closed. So that's what's called lower semi-continuity. So continuous functions are lower semi-continuous just because, well, this is a closed set over the real line, so its pre-image must also be closed since f is continuous, right? Okay, so theorem. If I have a lower semi-continuous function, then there exists a point in X such that f of X star is equal to the infimum. So, okay, so this is for a more general class of functions, which are these lower semi-continuous functions. Why is this a nice class to work with? Well, it turns out that especially for infinite dimensional problems, I mean, problems like about the shortest curve connecting two points over a surface or something like this, it's very rare that the functions we consider, in this case the length of the curve, are actually continuous, but they are oftentimes lower semi-continuous. So this is a nice realization. This is also, as we're going to see, the only property we need in the proof. But one thing I want to mention is that if f is actually continuous, then not only it's lower semi-continuous, but minus f is lower semi-continuous. So we can prove that both the infimum and the supremum are achieved by points in x. Okay, so for continuous functions, you can say there exists a point that achieves the inf, and there exists another point or potentially different point that achieves the sup, right? So, and that's going to be very important for us later, that both the infimum and the supremum are achieved in any topological space. Okay, how do we prove this? Well, we're going to use this finite intersection property. So it's great that our definition of lower semi-continuous is in terms of closed sets. Right, and my collection is going to be this collection here. F sub t greater than the infimum x f of x. Why do I take this collection? Why this condition, right? So the main point is this. So suppose I have a t that's greater than infimum. I claim that then the set f sub t is non-empty, right? Why is that? Because if t is greater than the infimum, t is not a lower bound for the values of f. Therefore, there must exist an x, right? So if t is greater than infimum, t not lower bound, therefore there exists an x with f of x less than t, and therefore f sub t is non-empty. Right, so okay, at least I know that individual sets in this collection are non-empty. We're going to use the finite intersection property, right? So I'm going to check that actually any intersection of finitely many sets in this collection is non-empty. And how is that, right? So what do these finite intersections look like? Well, I'm going to take different values t sub 1, t sub 2, t sub 3, up to t sub k for some finite k. And I'm going to look at the intersection of sets over here. Okay, what is that? So that's the intersection of free images and when you have an intersection of free images, we saw that at some point. That's the same thing as looking at the preimage of the intersection. Well, and I just argued before that the intersection of semi-infinite intervals like this, right, when I proved that the real line is not compact, I noticed that the intersection of intervals like this is just an interval with an endpoint that's the minimum of the TIs. And this is just f of the minimum of TIs. So everything that I did here is completely general. If I have t sub 1, t sub 2 up to t sub k, the intersection of the FTIs is just f of the minimum. Now, assume that t1, t up to tk are all greater than the infimum, right? So assume that I took a finite subcollection of sets in this collection of closed sets. In that case, I'm taking t1 greater than the infimum, t2 greater than the infimum, and so on and so forth. Therefore, the minimum of t1, t up to tk is greater than infimum, right? Because if I have a minimum of k numbers and they're all greater than infimum, their minimum, right, so is also greater. So this intersection is not empty if the ti are all greater than the infimum of f of x. Okay, now watch. Well, okay, so we have a collection of closed sets, and we just noted that any finite subcollection has a non-empty intersection. The finite, we know that X is compact, so it has a finite intersection property. So let me call this 3, and this is, this is 1. So the guy below actually implies that the intersection of all f sub t in this collection, t greater than infimum, is non-empty. And therefore, there exists an x star in this intersection, right? So what is that? It's an element of x such that f of x star is less than t, less or equal to t, for all t greater than the infimum. Notice that in principle it could be that the infimum is minus infinity, right? We don't really need to worry about that. But maybe the blackboard's a little bit messy. Let's make clear that we understand what we just proved, right? So we proved the finite intersection property here. And we proved that finite subcollections have non-empty intersection here. Now we know that the whole collection must have non-empty intersection. What does that mean? It means that there's an x star belonging to all of these sets. And what does it mean to belong to f sub t? It means that f of x star is less than t. And what does it mean to belong to the intersection? It means that this holds for all t that are greater than infimum. Okay, here's something that we know, right? So f of x star has to be greater than infimum. And it cannot be greater than any number larger than infimum. So, well, call the infimum I temporarily, right? So I'm saying this number, f of x star, is greater than or equal to I, and it's less than or equal to any number that's greater than I. And therefore, f of x star has to be equal to this I, to this infimum, and it satisfies this property. So just to go through again what we did here, we wanted to use this abstract definition of compact sets to prove that all continuous or lowest semi-continuous functions, if you want, achieve their infimum. So for that, we use the finite intersection property that deals with closed sets, so we better have some closed sets. These sets are closed for OT. I have a collection here of closed sets, right? It's just taking t greater than infimum. These sets are all non-empty when t is greater than infimum, right? Because again, t greater than infimum means that there is some x in the space x that has a value of f smaller than or equal to t. And it turns out that any finite intersection of these sets f sub t with t greater than infimum is another set f sub t with t greater than infimum. So any finite intersection of sets in this collection is non-empty. Therefore, by the finite intersection property, the whole collection has an empty intersection. And what we argued here is that any point in this intersection must achieve the infimum of f. And this is how we prove it. Again, we did just for infimum for lowest semi-continuous. If f is actually continuous, both the infimum and the suprema are achieved. And that's going to come up in our next video very quickly. And it's going to be one of the main steps in proving a series of equivalences for compact metric spaces. Okay, but for now we're done. Thank you.